Let me quickly talk once again about all of this. So imagine I have two locations A and B, okay, and from A to B I can transmit some data, the binary data, okay. So you can treat this this thing as a network actually. So A is a location, it's a sender of the data, while the B is the receiver of the data, while this middle line is a channel or the medium through which the data is going from A to B. Okay. Now, as I said that a binary kind of data is being transmitted from A to B, so you will say that either 0 or 1 is being transmitted from A to B. Now, there can be two types of errors that can occur actually. The errors that can occur are going to occur because that when you, for example, sent 0 from A, so there is already a disturbance or a noise, okay, in this channel which is added into 0, and you detected, that number to be 1 at B. So 0 was sent, but there was a noise, a disturbance in the channel, and due to this disturbance, something else was detected by B, and that something else is 1. So we sent 0, but 1 was detected. Or we sent 1, and due to this channel noise, 0 was detected. Now, how to deal with this situation? So what mainly we will like to do is that I will like to compute the probability of happening this and probability of happening this. Probability of happening this error and probability of happening this error. Okay? That we sent 0 but we detected 1 at B, or we sent 1 from A but we detected 0 at B due to the channel noise actually, due to the disturbance. Okay, it happens in an everyday communication. You want to say something, and if the signals are not good, some person is like hearing a distorted noise actually, okay, distorted voice, okay, distorted messages being transmitted from one place to another place. So what is the remedy? The remedy that the clever engineers have thought that if you want to transmit 0 from A to B, -2 will be transmitted. Okay, so for transmitting 0, -2 will be transmitted. Okay, and for transmitting 1 from A to B, 2 will be transmitted from A to B. So instead of transmitting the 0 and 1, let's transmit -2 or 2. Let's call these values x. So x is what is the value that is being transmitted from A to B. So according to this strategy, the x could be either +2 or -2. So if you want to transmit 1, you will transmit 2 from, what do you call, from A to B, and if you want to transmit -2, you will transmit 0. If you want to transmit 0, you will transmit -2 from A to B. Now, okay, you transmitted a 2 and -2 from A, but the question is, in the channel again you have noise, and you're gonna receive something else at the, what do you call, B actually. Okay, so imagine we received the value R at location B. Okay, now this R can be what? Your original value, that can be +2 or -2, plus some noise. And this noise is a random noise actually. So what is usually being assumed that this noise is a normally distributed random variable that takes values between with the parameter 0 and 1. Okay, so noise could be anything. And then what is being said that, okay, if this number, in other words, your value plus noise is bigger than or equal to 0.5. This noise can be in fractions. Okay, x is -2 or 2. but this noise is going to be a fraction actually. It can take any value, okay, from minus infinity to infinity, because it's a standard normal random variable. Now if r is bigger than or equal to 0.5, then 1 was transmitted. So this is like, okay, your resultant value, if this resultant value is near to 1, so if some number is, the received value is bigger than or equal to 0.5, okay, then this is near to 1, so we will detect basically that, okay, 1 was transmitted from A. And if R, in other words, your sent value plus data, the normal, what do you call, error, or not error, but the noise, if you receive this value R, and this R was received to be a value that is less than 0.5, so something that is less than 0.5 is more closer to 0, so we're going to say that, okay, 0 was transmitted from A, and 0 was transmitted from A. Okay, 0 was transmitted from A, and we detected 0. So here's the interesting thing. So R is x plus 1. So if the received value is bigger than or equal to 0.5, we're going to say that 1 was transmitted from A. And if R is less than 0.5, we're going to say that 0 was transmitted from A. Question is, this is a random value. Even by looking at the value R, okay, by looking at the value R, there are chances that you will detect otherwise actually. In other words, you sent 0 with this strategy, you sent 0, but at B we detected 1. And we sent 1, but at B it was detected to be 0. So we call this as a type 1 error. And I call this as, for example, the type 2 error. That's what I have written here actually. So there can be 2 type of error in this transmission, that 1 was sent but 0 was detected, and 0 was sent but 1 was detected. Now 1 was sent but 0 was detected. How this will happen? This will happen if opposite of this happens actually. Think about it. So if your R value is bigger than or equal to 0.5, we will assume that 1 was transmitted. But if this is an error, then what would be the complement of this? So you're going to say that 1 was sent but 0 was transmitted, so that's a type of error. This will happen if your resultant value, okay, because 1 was sent, so you're going to have x as 2 plus n, but this is less than 0.5. Because if this 2 plus n would be greater than or equal to 5, we're gonna basically correctly detect actually that 1 was sent and 1 was received. But if 1 was sent but 0 was received, and what is the probability of happening this error? So this will happen if 2 plus n, because 1 was sent, plus n is going to be less than 5. In other words, the opposite of this happens. While 0 was sent but 1 was detected, this will happen since 0 was sent, so the value of x would be negative 2 plus n, and since 1 was detected, so this value should be bigger than or equal to what you call 5. In other words, the complement of the opposite of the second condition. Okay, so these are the two types of the error that can happen actually. So now what we would like to do, what we are interested in actually. So we are interested in knowing the probabilities of happening this with this model. Okay, I'm interested in computing the probabilities of this with this model. So this model obviously would be a good model if there is a very less chance of happening this and this. Okay, there's a very less chance of happening this and this. So if there is a less chance of happening this and this, then you're going to say that, you know, the model is a good model. So let's see that what we get. Okay. Now, what is the probability of error, say for example in first case? In other words, 1 was sent but 0 was detected. So the error when 1 was sent. Okay, so the condition when 1 was sent. So this is going to be equal to, when it is going to happen, if this happens, 2 plus n is less than 2 plus n is less than, what do you call, 0.5. And this is same as n is less than minus 1.5, and this would be the value minus 5 of 1.5. So when we'll compute it, it turns out that it is the value 0.0668 actually. Okay. So let's compute the other case. So what is the probability of error if 0 was sent from A and 1 was detected actually? Okay, what is the probability of that error being happening? So this will happen if minus 2 plus n is bigger than or equal to, what do you call, 0.5, and this would be same as probability of n bigger than or equal to 2.5, and this would be same as phi of 2.5. Okay, and when you will compute this, not phi of 2.5, so this would be 1 minus phi of 2.5, and when you will compute it, so what will happen is that this would be 0.062. Okay, 0.062. Now here's an interesting question. What is the interpretation of these two numbers that we have obtained? So with this strategy, so the fundamental question was, with this strategy, what is the probability of this error and what is the probability of this error? So the probability of sending 1 but receiving 0 is 0.6, or if you round it off, can be worst 7 actually. Okay, so what does it mean? It means that on average, out of 100 sent messages, or 100 times sent, for example, 1, only 7 times there will be an error actually, or only 6 times there will be an error, 7 times if you round it off. Okay, so for 93 of the time there will be no error. This strategy will correctly detect 1 being sent and 1 being received, but there will be only 7 out of, on average, only 7. There are only 7 times that the 1 would be sent, but the 0 would be detected, and otherwise the first error would happen. And similarly, the interpretation of second. So what is the probability that you sent a 0 but 1 was received? That is even lower actually. Okay, that the probability of happening this is 0.62. In other words, if you send 100 zeros from A to B, only 6 times this strategy can give you an error actually, or this algorithm can detect the 0 incorrectly, which is very low. 94% of the time this algorithm will work and you will detect the 0 correctly. Okay, So this is another interesting example of what do you call normal distribution actually. So there are more. I'm leaving some examples and exercises for you to do. This is what that you have to something do, but I'm just dealing with the non-trivial example, the more serious and more interesting examples. I hope like all this calculation makes sense to you. You can read more from the book and have a sense, or we can have a discussion in the Zoom session. Okay. Now, I would like to move towards another powerful thing that the normal distribution can do actually. It's very powerful. Okay. So I'm going to write a theorem that is, and I'm not going to prove it, because this theorem that I'm going to write is a particular case of the central limit theorem. The central limit theorem would be probably the last topic of our discussion, so I'm deferring its proof. We'll do its proof so this would be a kind of a particular case of the central limit theorem, okay, which essentially says that if you have lots of random quantities, staked at one place, then those their sum is always going to be normally distributed. We'll talk more about it in detail. So here's a theorem, and this theorem will do what? This theorem will make your life hell easy if you want to do computing actually. Okay, if you want to compute the probabilities. So here's the theorem which is called de Moivre and Laplace limit theorem. Okay. De Moivre-Laplace limit theorem. So what does the theorem say? Theorem says, imagine you are doing n independent trials, okay, n independent Bernoulli trials, okay, and Sn represents the number of successes in n independent trials, and independent trials, Bernoulli trials, with each success probability, so in each of the independent trial, with each resulting in success, okay, success with probability P. So we did n independent trials, and each of the trial there is a probability P that we will get a success, and Sn represent the total number of successes on those n trials actually. Now, what I would like to do? I would like to say, what is the probability that Sn, obviously this would be a kind of a situation of, okay, if the trials are Bernoulli trials, this would be a kind of a situation of binomial random variables actually. Okay, this would be a situation, kind of a situation of the binomial random variables, in which the mean is going to be, what is going to be the mean if there are n independent trials, and what do you call, P is the probability of success, the mean is going to be NP. And what is going to be the standard deviation? The standard deviation is going to be the square root of NP and 1 minus P. Okay, so these are the two facts about the binomial random variables. So if you have this Sn, that is basically the total number of successes in n independent trials, and you standardize it, and by standardizing it, what? Subtract mean out of it and say divide it by the variance of it, so np1 minus p. And what is the probability that this standardized Sn, which we got by subtracting mean and dividing by what you call standard deviation, stays between A and B? Okay. Now, the typical way to do is what? That okay, this would be a kind where A and B are two numbers. Okay, these are two real numbers. So the typical way is to start a sum from A and end that sum at B. Okay, that could be a big sum actually. Okay. But what does this theorem is telling you? You can approximate this probability would converge to phi of B, where the phi of B, phi is the standard normal distribution, phi of B minus phi of A, okay, as n goes to infinity. As n goes to infinity. Okay. Now, so what does the theorem is telling you? Let's reflect a bit on this theorem. Imagine you have n independent trials, and each of the independent trial there is a probability of success P, and Sn represents the number of successes. Now, what is the probability that your Sns roughly, or your number of successes, standardized number of successes, are going to be between A to B? Now, a direct way to compute the probability is to, write this as the sum of lots of probabilities and compute each one of that value and then compute this probability. But this theorem is telling you, if you have this and your n, in other words, you are doing more and more trials actually, then there is no need to compute a big sum of the probabilities. Just compute phi of B minus phi of A. In other words, just compute the phi at B and phi at A, and you will get this probability, because this probability is basically approaching to this as n goes to infinity. So in other words, rather than computing this big sum, compute these two simple numbers. Go and look at phi of B from your table, and go and look at phi of A from your table, and compute their difference. You're going to get this probability. आपको लंबी जो है वो calculation करने की ज़रूरत नहीं है, ठीक है? As I'm not getting into the proof of it, I'm gonna do the proof of this when I'm going to do the central limit theorem. We'll prove a central limit theorem. This would be a particular case of the central limit theorem, so I don't need to do the proof. So let's okay, one thing. This will happen, in other words, this probability will converge to phi of B and phi of A if n is getting bigger and bigger and bigger. So that's an important thing. This probabilities would not work for smaller n. The n has to be a bigger number. Okay? The more smaller n you have, the more error is going to be between these two numbers, this probability and this probability. Okay? But you'll have a rough estimate. So let's do some examples and let's see that how this interesting thing can help us in a variety of situations. So here's an example for f. Example for f from what do you call? Example 4f from Ross. So imagine a coin is flipped. So I have a coin is flipped 40 times. Okay, so you flip a coin, quite a big number.